Silicon is a brittle metal. It has a slightly grayish change and it's a solid at room temperature. It was first isolated in 1823 by John Berzelius following a failed attempt by Sir Humphrey Davy in 1808. Today, silicon encompasses the basics of most modern electronic circuitry, as well as many, many other uses. It's accommodated for by its vast abundance in the Earth's surface, in the form of silica and silicate minerals. Over the course of this educational video, my fellow colleagues and I will be trying to add some more depth to your understanding of silicon. Who knows, you might even find you have a bond.
Hello everyone, now I'm going to be showing you how to solve a question using the E equals HV. So as you see, the question reads, green light has a frequency of 3.01 times 10 to the power of 14, and what we need to find is the energy itself. So as you see, V equals frequency, and what we need to find is the energy itself. So what's given to us is the frequency 3.01 times 10 to the power of 14, which is the V. And what we want to find is the energy, E. So the equation is E equals HV, and the H is the Planck's constant, which is 6.626 times 10 to the power of 34 joules per second, times the frequency V, 3.01 times 10 to the power of 14. So we plug that in the calculator. So if you do that, you'll get the energy, which is E equals 1.99 times 10 to the power of negative 19, and the unit is in joules. Thank you.
Hello everyone, my name is Salman Murray, and I'm going to be explaining to you what the electronic configuration is. So first of all, every element on the periodic table consists of electrons, protons, and neutrons. But in this situation, we'll be concerned about electrons itself. First of all, electrons exhibits of negative charge, and it's found in the nucleus itself, around the nucleus itself, because it's going around orbitals. So there's some about the electronic configuration. There's set of orbitals which are S, P, D, and F, and they all have different shapes, and one orbital can hold the maximum of 2 electrons only. The P and D and F orbitals have different sublevels, unlike the S orbital, which can only hold 2 electrons, and thus can hold more electrons. Like, for example, the P can hold 6 electrons, the D can hold up to 10 electrons and a minimum of 1, and the F can hold even more. Okay, so there is also an order for the levels filled in all the orbital sublevels. And as you see, the order is shown in the whiteboard here. So the order goes on as 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, and then 3d to the power of 10, and the pattern goes on to the 7p. As you see, the S, as I said, can only hold 2, the P can hold up to 6, and the D can hold up to 10. Okay, so also the coefficients of the shell itself, the S, the P, the orbitals, and the D. For example, the 1 represents the first shell of the element, and so the coefficient 2 represents the second shell, the third represents the third shell, the fourth represents the fourth shell, and so on. So it's basically showing the shells of the element itself, and the charge and the 6 here, and the 2, and the 10 and the D, the orbital of the D. It also shows the number of electrons in the element. So the exponents in here are basically the number of electrons in the element. So if we add all the exponents together, it will give us the total number of electrons in the element. So using that, we can identify the element itself just by looking at this pattern. So just to help you, I'll be giving you an example so you can know how to write the electronic configuration for each element. So, for example, I give you the carbon, which has six electrons in it. So, to write the electronic configuration for it, we do carbon, 6 electrons. So the electronic configuration for it would be 1s squared, 2s squared, 2p2. So how do you know that this electronic configuration is related to carbon? Is by adding all the exponents together. So 2 plus 2 plus 2 would give you 6, which is the number of electrons in carbon itself. And the 1, 2, and 2 represents, which are the coefficients of the orbitals, are the number of shells that carbon has, which is 2 shells only. So there are 2 exceptions for the rule of the electronic configuration, which I explained with carbon just a moment ago. So the 2 exceptions are with Cr and Cu. Cr is basically chromium, which has 24 electrons. So if you would normally people would normally write the electronic configuration for it as 1s squared, 2s squared, 2p6, 3s squared, 3p6, 4s squared, 3d4. That's actually wrong because the 3d to the power of 4 is halfway filled. It's not even halfway filled because the d can take up to 10 electrons in the sublevels, and the halfway filled is 5. So here it's 4, so you need to make it halfway filled, so you need to give it 1 more electrons to be 5. What you basically do is take 1 electron from the 4s squared before it, so the 4s squared would basically be 4s to the power of 1 and 3d to the power of 5, so it can be halfway filled. So for the second exception, except from chromium, we have copper, which is the symbol for it is Cu. It has 29 electrons. So if you would, people would normally write the electronic configuration of it as 1s squared, 2s squared, going to 4s squared, and then 3d9. Because as I said earlier with the chromium, the 3d, it has 9, which is 1 electron away from being fully filled. So what you need to do is the same as chromium. You basically take 1 electron from the 4s squared, and then you would write it down again, so it will be 4s to the power of 1 and 3d to the power of 10, so it can be fully filled. So that's the correct way of writing for copper and chromium. Here's a fun fact for you. Did you know that you can determine the number of electrons using the equation 2n squared, where the n is basically the number of the shell number, and you basically substitute it here. I'll give you an example. So the equation is 2n squared. So you substitute the shell number to determine the electron. So for example, the first shell, you basically say 2 multiplied by 1 to the power of 2, which gives you the electron number, which is 2. And then you can do this to the other number of shells. For the second shell, it would give you a number of 8 electrons.
Did you also know that this relates to ionization energy? The ionization energy of silicon is 81,573. The atomic number of silicon is 14. That means that the number of protons, electrons, and neutrons are pretty much equal, being 14. These boxes represent the shells and the electrons inside them. The first box represents the first shell. The second box represents the second shell. And these two represent the 2p to the power of 3. The arrows are this way up and down because they show how electrons are moving in the opposite direction. The main thing that has to be taken into consideration are these last 3. This is because this shows how this is stable because the boxes are half full, and that means that they would require more energy to get rid of them. However, in the case of oxygen,
This is
In the case of oxygen, in the last boxes, we have one extra electron more, and that means that it's not half full and that it's not stable. Therefore, the energy required is less, because it wants to get rid of it and make the elements more stable. The ionization energy of silicon is 81,517. The atomic number is 14. Ionization energy are cross periods that relate to electron configurations. Basically, the higher the proton number, the more the ionization energy of the element. The protons are located in the nucleus. Because the protons are positively charged and the electrons are negatively charged and are the opposite forces, they are forced to attract against the protons. The ionization energy required is increased as the number of protons increase. Therefore, when we look at the period of the element, we can determine the ionization energy required in order to pull the electrons away from the nucleus. The higher the proton number, the more the ionization energy is required. For example, natural gases, helium, for example, helium. The fact that its outer shell is full means that the ionization energy required is more. However, lithium or potassium have one electron in the outer shell. Therefore, the amount of energy required is much less. Deduction of the group of an element from a successive ionization energy data. For example, if there are 8 ionization energies given off in an element, and if the ionization energy is going at a constant pattern, from 1 to the 3rd electron being removed, and the gap isn't a lot, that means that it's following the same shell. However, as the gap between the ionization energies required to remove the electron is increased drastically and is prominent, for example, from 2000 to 11,000 ionization energy required to remove an electron, it means that the energy is of another shell, telling us that there are those specific numbers of electrons in the outer shell. If it takes 3 ionization energies for the gap to be prominent, it means that the element is in group 3. Silicon has numerous isotopes, and they have their own specific use. However, the main 3 ones are silicon-28, silicon-29, and silicon-30. Silicon-28's natural abundancy level is 92.47%. Silicon-29's natural abundancy level is 4.47%. And silicon-30's natural abundancy level is 3.27%. Do you know what this means? Check out the website.
Every element has specific features that separate it from the others. This identity can be spotted in multiple forms. The most common difference would be the number of electrons, of course. An element with a total of 6 electrons is surely carbon. We know this as certainly as we know that helium has a total of 2 electrons. But in real-life situations, we aren't provided with the number of electrons that an element has, and different methods have to be used to identify elements. In CSI shows, you always see a process that includes retracting fingerprints and searching for matches on a database. The fingerprint is unique, possessed by only one person out there, and due to this fact, we can match that fingerprint to a specific face.
So what do you have for me today? There you have it. You've got our guy.
similar process is used with elements. The most basic form of this process is called the flame test. An element is set on a flame and the atoms are excited, ultimately resulting in the element releasing photons or light. This makes the flame appear to be another color. For example, one element might turn the fire yellow while another would turn it purple. But when there are so many different elements, it becomes difficult to tell the difference between those just due to that flame test, because it can't be accurately picked up on by the naked eye, and a more complex form of the flame test has to be used. Now this process is called the atomic emission spectroscopy. Now as can already be deduced from this, this only provides qualitative rather than quantitative data. Now as any art student knows, whenever different colors of different wavelengths are mixed together, you'll have the result being one large color. And that's why the flame test isn't always that accurate, because the different colors mix in and then you have a hard time telling the difference between a color of the fire whenever it could be, for example, orange or light red. So for this, we use this setup, essentially, and it includes a Bunsen burner in this case, or really any provider of energy that will excite the electrons, followed by a small box that only allows a narrow selection of light in, with a prism, and finally a small sheet of paper. Now the way that this works is that the element is placed on the fire, and after the electrons are excited, what will work is that they will go from their ground state to their excited state. Now whenever electrons are excited, the problem with this is that they become unstable and they must emit energy. So what happens is they emit energy in the term of photons and they return to their ground state. And this allows the color to be given off. So for this state, we're just going to say for the case of this one, that the flame was blue. Now the flame is blue. We've got our light traveling through here. And through the narrow tube, we only get one small ray of light. And then it will get to the prism. Now, as we all know, in terms of the prism, this will slow down the process because of the different wavelengths of the color. So, for example, we're just going to say that this specific element, element X, whatever, will break into blue. It'll break into red. And just for the sake of this, we're just going to say it breaks off into black, when in essence it really doesn't in real life situations. So we've got blue, black, and red. Now for after it leaves the prism, it still remains in this broken up state, which means that we can just continue this on, continue the black marker on. That leaves a black mark, the blue leaves a blue mark, and the red will leave a red mark on the paper. And the reason this is significant is because rather than one large color, we actually have the separate wavelengths used in this process. And the interesting thing about this is that each and every single element, when put through this process, will give a different result. So this will essentially create the identity of each and every single different element, because no element will produce black, blue, or red other than element X, and that's how that works. This represents the identity of an element, as each element provides a completely unique result. But not only does this provide the face of an element, but it can also help to give us an idea of the energy levels in that atom. When the electrons are excited, more energy is present, and the result of this is that the electrons move further away from the nucleus, using the energy as a resisting force against the pull of the nucleus. However, the electrons cannot remain in this state for a long time as they become unstable. For this reason, they return to their ground state, resulting in the emission of energy. This energy correlates to a specific wavelength and then shows up on a line on that spectrum. When electrons return to the first shell, the energy wavelengths correlate in the ultraviolet region, given that it took the most energy to pull the electrons away from the nucleus in the first shell. When electrons return to the second shell, it gives off energy in the visible light spectrum. And lastly, the infrared spectrum starts from the third shell going onwards. Due to this phenomenon, the atomic spectrum can be used not only to identify elements, but to understand the energy levels within the atom. But what happens after the fourth or the fifth shell when the shells keep on growing further away from the nucleus? Well, the energy levels become more closely spaced out until eventually they converge at a high potential energy. This is known as the convergence limit. At this point, the spectrum is no longer a line spectrum and it becomes a continuous spectrum. In the electromagnetic spectrum, there is a direct relationship between color, frequency, and wavelength, which is most simply described by the following rule. Frequency and wavelength are inversely proportional. The science behind ionization energy is that at this distance, the nucleus is no longer strong enough to attract the electron, and it moves freely without restriction. Then this links back to the concept of ionization energy, because at this convergence limit, the atom loses its electron, becoming ionized. Ionization energy can be found with the difference of the convergence limit and the ground state of the electrons.